I think we are. I miss, you know what I miss? I miss a way to just share these with everyone, you know. Twitch.tv, certain systems. 4-year. Do you have hashtags for these? 4-year. Senpai. 4-year transform. Who follows these hashtags? I think nobody. Quantum mechanics, probably. Quantum mechanics. Yay. Tweet. I should have a more original way to do that, but let's anyway. Where are we? We were doing 2.1b. Yes, we were doing these, baby. We were doing what were we doing? So we were doing the Fourier transform, and I just forgot even what the page was. I mean, that's definitely the book. So let's go back to the exercise. So this is exercise 2.2, and we're doing B. So we want to show that the probability density of finding the particle momentum is isotropic. Probability density of finding the particle. So we need to do two things. We need to go to, we need to kind of translate that into the translate these Python x21b. So that's better. we have this expression, and we want to go, we kind of want to go, I don't know if I should actually use the I don't know if I actually should use the end that I found, or I don't care. The solution doesn't seem to care. So, but yeah, basically but I just don't like, I think SymPy, the challenge with SymPy is that it's quite verbose, and so I think it's important that you what I'd like to figure out is how can you kind of make sure that you don't go all the way with all these different piecewise and whatnot, like options, because if I now print this stuff, which is essentially so QM position momentum Fourier transform. Like okay, so this is what I was following. So this is what I was following from K to P. This is a variable. What does it do? I don't know. We get the Fourier transforms in terms of X and P. So this is what we want to get. Dx. This is what we want to get. If we define UPX to be the state with definite momentum, P, okay, so P is the momentum, right? In position space, our formula is similar to the state in momentum space with definite position X. What is the difference? Oh, the sign. The states cannot be normalized, but they do have a normalization convention which is satisfied due to the constant shown. Okay, so that's just the way you represent the state. So what they're saying is if you multiply the position, no, the momentum representation times the position state, no, the momentum state, then you get the position if you integrate. Okay. I'll have to, so there's definitely something to explore here in terms of why the exponential, but I'm trying to at least, let's try to get something sane out of that, because if I do this thing, well, I get something truly bizarre, which I don't like. I didn't even know how to read that. It's square root of 2 times the integral times 0 I don't like, I just don't like this whole, I see that. Okay, so this is just huge. Okay, that's stupid, right? So this is like, it gives you, SymPy gives you like, well, it's 0 if all these apply. I just don't want that. Why would I want that? It's like these is like, and these or these is like a huge thing, which probably is like self-explanatory if you just keep these here, right? Because essentially what we have here is what I just wrote. So yeah, that's fine. I just don't like integrate piecewise, avoid. So SymPy avoid piecewise results from integrate. Like, hey, can I just symbolic integrals? So integrals modular implements methods got definite and infinite integrals expressions. Personal method, integrate. Exactly. SymPy can integrate a vast array of functions, polynomial functions, rational functions, integral transforms, definite integrals, integral transforms, whatever that is. But I just don't like the. Okay, so definite improper integrals often entail delicate convergence conditions. Pass cons piecewise, separate or none, to have this returned respectively as a piecewise function, as a separate result, or not at all. Okay, so maybe that will just. So this is what that's with all these different. That's good to know. That would be cool. Integrate. So can I just do cons none? Is that good? Is that a good way to do this? Let's see. Oh, but then it just goes to 0. Separate. Piecewise separate or non, that is returned. Definite improper integrals. Indefinite integrals are returned without terms that are independent. independent of the integration variables. Antiderivative. Delicate conversion conditions. Pass counts piecewise, separate or non to have these returned, respectively as a piecewise function, as a separate result, or not at all. But then it returns me. Then it returns me. What does it do if I do that in exercise 1? By the way, I non. Index on range. Sorry. Interesting. And actually, simplify. I'll just get rid of simplify. But it seems like that turns into something quite interesting, right? Oh. Square root of 2 times square root of 8. Okay. Conditions none. Separate. So we're learning something here. Step 2. Okay. Piecewise. Am I doing something wrong? Otherwise, integrate and solve. But then solve breaks. Invalid non-comparison. I definitely have to dig more into how the integrate method. That's interesting. Cons non. It's definitely interesting. I have to probably deep dive into these a bit more. I should just probably keep it as a note here. So because yeah, the problem is it gives me 0 in this case, right? One be separate, not separate, but non. Separate but non. It gives me 0, and that's I don't like. If I don't give it ranges, and I keep it indefinite, and baby's crying, so I think I have to go. Ooh, interesting. That's definitely interesting. I don't get how that works well with indefinite, definite, and whatnot. Here they do definitely indefinite, and then, but yeah, I don't know. Yeah, I think I have to guys drop it here and then come back later today. But it doesn't sound good in baby world. So anyway, but okay, I learned something. So this parameter here, and something to do with this. I'll try to think about this a bit more throughout the day, and then see if I can come back to this. Multiple of differentiation with respect to x. That's interesting, right? It's not the Fourier transform. It's just maybe it's a convenient way to do the transformation. Is the operator of multiplication by x, whereas momentum is a multiple of differentiation with respect to x. Definitely have to try to understand that. But I don't even know what would I like to see out of these, because the way the momentum wave function is defined, like the integral, whatever it is that they do here. What I want to show is like, maybe it doesn't matter if it's exactly, if you're getting exactly these results or not. Because what you want to show is, you want to show, okay, so what have they done? Well, we have taken the z-axis of the integration variables to coincide with the momentum direction. What? Okay. So there's something else here you have to do, which is take an axis, an integration axis. This is kind of what I might be missing as well for these, right? It's something to do with the integration axis. It's something with the fact that position is three-dimensional, but here we have an R, right? And then maybe the reason there's no R in here is because you're integrating along x, and you pick an axis when you do that. You know what I mean? And so then R just becomes a constant or something. You don't. It's not. You're not doing a differentiate, sort of an integral on R. You're doing an integral on x, because that's how the function is defined. But then again, you have to pick one axis maybe, or I don't know, or you actually have to do all the different axes. Maybe that's what I'm doing wrong here. Maybe that's what I'm doing wrong here. And then this just becomes more of a constant. This bothers me a lot, because there's no R in here. So I don't know. And here is like, okay, so this kind of makes sense, and I think that's basically, you know, what you would get here. Is just that if you do these, you know, that actually does me it actually makes the integration. Can I simplify? Or it's gonna break? Okay, it simplified it like this. Whatever that is. But it's funny because now it doesn't have an R. It's just dependent on P. No, it actually does have the R here. Which is essentially, this thing here is essentially the same like these here. We have taken the z-axis of the integration variables to coincide with the momentum direction. How? And again, it's an integral on x. Not an R. It's good. I mean, it's good that this exercise is the one that we're doing, because it's just so damn, like, this is exactly the things where, and I think that is the same thing that I might be missing here, is that R, like when you're doing that, you're really, that's not what you should be doing. You should be doing an integral on an x or something like that. Here they do an integral that is based on x, you know. is they're integrating through X and not R. How the heck do they even get that? How? Is it they just go and do these simply? IPX, and so they just go ahead and say this is not, this is X, right? So we have another symbol which is X, and then this is basically IPX, and then R is already in here, right? So if you do that, then you get these here. Okay, it's a bit better. It actually has integrated it though. That's what's, and here they do 0 to infinite. Well, they say it's proportional to these, but that's something that I don't think SymPy will ever be able to help me do, right? Why? I'm failing to see if that's the same. How do they even get these? How? And D3. What is integral D3x? So is this because of the 3 dimensions? For triple integral. Oh, yes. Yes. Of course I didn't know what that meant, and after Googling I realized, okay. No. Oh my god. So you integrate across all. Maybe that's where the 3's even come from, you know? No. Why? Maybe that's where these things then come from, right? The 3's in here. I wish I had some more detailed steps to go through. And how do you do that? How do you do like triple integrals in SymPy? Triple integral. Isn't it you just do integral of integral of integral? Oh. No. Okay, so triple integrals is the thing. What's the concept of a triple integral though? It's because you're doing, because this is probably what we have to do here as well, you know. That is why this is not giving me these. And again, treat R then as a constant. So it turns out that maybe moving to the next step is gonna help me solve these ones. So the first step. So, you know, like, I don't know, if I do these and I say integrate x, right? Just let that like these. Why is it complaining? Why is it complaining? A. 0 to infinite. I don't think that's how I have to do this. I think I have to do this kind of XYZ thing. Like, okay, that's definitely something to explore. But I'm happy that I found these out, at least. Check. I'm happy that I found these out. Triple integrals. Triple integrals. And then these R is just... It's funny because actually then these R is really something that you have to express maybe as... Maybe... Oh, maybe do we have to express R as a function of this of x plus y plus z? Probably. Maybe that's why there's no R in there. I don't know. I don't know. But anyway, some mini progress. See you next time.